All right, so now we are looking at this problem 9.16, which relates to finding the partial pressure of a gas. You are given the total pressure, and this is a system in which the gas is collected by the downward displacement. So let's assume you have a reactant. Basically, it is decomposing and it's giving you a gas, and this gas goes through this pipe or through this tube, and it's collected by the downward displacement. So in this system, as I said, the water is wet. The gas is wet because it is collected over water. And when it passes through the water, yes, it pushes the water down, and the excess water gets collected in this trough. But in the meantime, it also has some of the water vapors, and these vapors exert their own pressure, and that pressure is the partial pressure of water. Partial pressure of water. So Dalton's law talks about that the total pressure that we see from outside, the total pressure of the gases we see outside, is equal to the pressure of gas 1 plus the pressure of gas 2. So in this case, there are two gases we have. One is the argon, and the other is the vapors of water, the water vapors, okay? And so when this gas was collected, as you've done this in the experiment in the lab also, so we have to note down the temperature. At what temperature was the gas collected? First thing, that temperature relates to a table. In a table, you will see the vapor pressure of water vapors, right? Water vapors at a very specific temperature. And so it's very important to note down, the temperature at which the gas is being collected. So specific temperature, you look into the table and note down at 26 degrees Celsius, what is the vapor pressure of water. So let's look at that. Okay, so going back to our PDF here. Okay, now if you go look up, this is the table. Now on the tests or something, we will provide you this value, but for your homework and for your quizzes and all, you can look here. So you see the temperature is given and the pressure of water is given in, vapor pressure of water is given in these torrs. The unit is torr. So we are looking at 26 degrees Celsius, it is 25.2. So at 26 degrees Celsius, the vapor pressure of water, or that's also the partial pressure of water in this case, water vapor, is 25.2. You see this 26 is 25.2. 25.2, and the unit is torr. Okay, so now going back, so you see this is the setup. So now here I'm going to just put here the total pressure is already given to us. We are being asked to find the pressure of argon, and from the table we have found the pressure of water vapor. Okay, this water vapor, now we're going to just plug in these numbers. Now important thing is that important thing is just make sure that these units are the same. So if this is torr, this is already torr, so you're good. Otherwise you will have to change it. Okay, so pressure of argon plus for the water vapor, it is 25.2 torr is equal to total pressure is 760 torr. Okay, so basically 760 torr minus 25.2 torr. What do you get? What do you get? 760 minus 25.2 torr.
734.8.
734.8 torr. Okay, so this is the partial pressure of argon. Okay, and that's the answer. All right, guys. Okay, so now we're going to look at the learning check problem in which we are given oxygen. We are given the values of total pressure 764 torr, and the total pressure actually contains the pressure due to oxygen, the partial pressure of oxygen, and the partial pressure of water. So oxygen is collected by the downward displacement of water, and we are trying to find what is the volume of the dry oxygen. What is the volume of the dry oxygen? And we are given the total volume, and we are given the total pressure. So total pressure is given, total volume is given, but we need to find the volume of the dry one. So that's without the water vapor. So how do we do this? So we know the formula, the Graham's law. Total pressure is equal to PO2, that's the P1 partial pressure of one gas plus the partial pressure of another gas. So here we will find the partial pressure or the vapor pressure of water at 29 degrees Celsius. So that we look at the table that is given to us in the book, and we find this from the table that at 29 degrees Celsius, the vapor pressure of water is 30 torr. So now we find so first is find the partial pressure of oxygen. Find partial pressure of oxygen. So you put it in the formula, total minus the partial pressure of water vapor, and you get the partial pressure of oxygen to be 734 torr. Now the next question is that what is the volume without the oxygen? The volume with the oxygen is 0.560. The volume without the oxygen is this one. So this is the dry oxygen. So dry oxygen, and this is the wet oxygen. So when the wet oxygen, so we use the Boyle's law here, two laws combined together. Boyle's law says that P1V1 is equal to P2V2. So you put the total pressure times the total volume, total pressure times the total volume, that's total volume, is equal to the partial pressure of oxygen times the volume when it's dry. So when you do the math, you get the answer as 0.5828. So the answer is volume of dry oxygen is equal to 0.583 liters. Okay. All right, let's look at the next one. So our next problem is about finding how many tanks of oxygen are needed. We are given the acetylene. The volume of the acetylene is 9,340 liters, and the temperature is 0 degrees Celsius and 1 atm. So these are the standard temperature pressure conditions, STP. So here they are saying find the volume of how many tanks of oxygen. Now you're also given that one tank of oxygen contains 7,000 liters of oxygen. So this is a problem where Avogadro's law is applied. So Avogadro's law is relating to volume and the number of moles. So volume, as the volume increases, the number of moles increase, or as the number of moles increase, the volume increases, and so forth. So here, the volume and the number of moles are interchangeable. So yes, we know 2 moles of acetylene are reacting with 5 moles of oxygen, but we can also say that 2 volumes of acetylene are reacting with 5 volumes of oxygen. So we know that it's 2 moles, but these moles and the volumes can be interchanged. And in the volume, you can put liters, you can put milliliters, you can put, whatever units for volume you need. So here, this is a strategy. You're first going to find the volume of oxygen that is needed for 9,340 liters of acetylene. So we use a simple conversion where we use these. These are the conversion factors coming from the balanced equation. So we take the volume, total volume of acetylene, and we convert it into the volume of oxygen using the conversion factor. And we get 23,350 volumes of oxygen. So these 23,350 volumes of oxygen would fit into how many tanks? One tank can hold 7,000 liters. So when we do this, we use this as a conversion factor. One tank is holding 7,000 liters. So 23,350 volumes would contain how many tanks? Can go in how many tanks? That comes out to be 3.33, 5, 7, and so forth. So when you make this becomes 3.34 tanks. So this is again given in the book as 3.34. Okay. All right, let's look at the next. Okay, so we are given this problem 9.18 where we need to find the volume of oxygen. We are given ethylene, which is 17.0 liters, and we are given the temperatures and the pressure. So here we are not given something. We are not, this is a combustion reaction where we are not given the reaction. So let's write the reaction first. So here is this guy is called ethylene. Ethylene reacting with oxygen as a gas is giving you carbon dioxide as a gas and water vapor. Okay, now here balance it. So first balance carbon, so 2 carbons, then balance hydrogens, 4 and make it 2. So now we have 6 oxygens, 2, 4, 5, 6, and we can make it 6. Okay. So 2 carbons, 4 hydrogens, and 6 oxygens. 4 coming from carbon dioxide and 2 from the water. So here we are focusing on the ethylene, 1 mole of ethylene and 3 moles of oxygen. This also means 1 volume of ethylene, that is, let me write this down as C2H4. C2H4 is reacting with 3 volumes of oxygen. Okay, this is one thing. Next is let's find the volume of oxygen. That's what the question is asking. So you're going to take 17.0 liters of C2H4, right, times the 3 volumes of oxygen over 1 volume of C2H4. So when this cancels out, you get 17 times 3, and that is 51. So 51 volumes, and 51 volume is 51 liters of oxygen. Okay, so here liters and liters, we basically liter volume and volume will cancel, but liters is what is left, and volume is the same. Okay, let's see. Okay, so we are doing this problem 9.19, and as I told you, this is going to be on the test. Why? Because it requires you, number 1, to balance the equation. So the question is asking you, you are preparing sulfur dioxide. You need to find a volume of sulfur dioxide. You're given the temperature in degrees Celsius, given the pressure and you're given the mass of sulfur. You're finding for sulfur dioxide, but you're given the mass of sulfur. Okay, so these are the 2 things. So here you're taking sulfur as a solid, reacting with excess oxygen. When we say excess oxygen, that means sulfur is a limiting reactant. Whatever amount of sulfur you are taking, that much maximum amount of sulfur dioxide you're going to produce. So here is this oxygen as a gas in excess. Okay, gives you sulfur dioxide. So basically here, when you balance the equation, it is 1-to-1 ratio, right? But sometimes you have to balance. Just make sure that you balance the equation. Okay, balance the equation, and in this case, luckily, it's just 1-to-1. Okay, so we are given, so pay attention to this. First thing, what are the steps that you're going to use? Number 1, you are given sulfur, and that sulfur, the mass of the sulfur given is in kilograms. So you're going to convert that into grams, and then from grams, you're going to convert it into moles. Okay, so that's one step. So you have the moles of sulfur. Next thing is you're going to convert the moles of sulfur to the moles of sulfur dioxide using mole to mole ratio, mole ratio, okay, from the balanced equation. So now you have the moles of sulfur dioxide. The moles of sulfur dioxide is equal to the value of N. And you know the formula, PV is equal to nRT, okay? We need to find a volume. So the formula we are using now is that V is equal to nRT over P. Now, pay attention that T is given in degrees Celsius. So you need to add 273 to make it Kelvin. So how much is that? 273 plus 343, and you get 616 K. So we are given the temperature, we are given the pressure. We know the value of R is equal to 0.08206 liters times atmosphere per mole K. Okay, so the value of R is known, the value of N is known, and we can find the volume of, we can easily find the volume. Okay, so let's do this strategy. All right, so here 1 kg. So first step, 1 kilogram sulfur times 1000 grams over 1 kilogram. That's the grams to grams conversion. So this comes out to be 1000 grams of sulfur. Okay, second step, you're going to take the 1000 grams of sulfur times moles of sulfur. So 1 mole of sulfur, what does it weigh? Look in the periodic table. Look in the periodic table and tell me, what does it weigh? Yes? Come on, guys. 32 grams of sulfur. Okay, so that comes from the periodic table. So 1000 divided by 32, what do you get? 31.25 moles. And these are the moles of sulfur. Okay, next comes the moles of sulfur dioxide. So 31.25 moles of sulfur times from the balanced equation, 1 mole of sulfur dioxide is formed when 1 mole of sulfur reacts. So 1 mole of sulfur dioxide over 1 mole of sulfur, and you get 31.25 moles of sulfur dioxide. All right, now we have the moles of sulfur dioxide, right? So volume is equal to N R T over P. So that's for the sulfur dioxide. So we need to find the volume of sulfur dioxide. So 31.25 moles of sulfur dioxide times R is 0.08206 liters times atmosphere per mole K times the temperature is 616 K over the pressure, and the pressure was 1.21 atm. 1.21 atm. So here we see that atm and atm cancel out, moles and moles cancel out, K and K cancel out, and you're just left with the volume, liters. So let's do 31.25 times 0.08206, right, times 616 is equal to 1579.65. 1579 9.65 over 1.21. Divide by 1.21, and that gives you 1305.5 liters. And that is a standard notation. You can write it in scientific notation by moving the decimal point. So this becomes 1.3 into 10 to the power 3 liters. Okay, and that is the volume of sulfur dioxide. Got it, guys? Okay. Okay, let's look at the next. Okay, what's the math here? Okay, I need a calculator for that one. Scientific calculator. Oh, come on.
It's at 0.29
Which one?
for the square root 28.
28 is 5.29.
Yeah.
Okay, and the other one 64 is 8. Okay, times 79. 79. So 5.29. So let me start recording it. Okay, so that is 4:1. So this is 52.23 milliliters per second. Okay, leave out, as I mentioned, you are leaving out. Let's just write this again. Leave out 9.21, because here they're wanting your time and all that stupid math calculations. Yeah, you leave it out in the extra credit. I mean, it's optional. Determining the molar mass using the Graham's law. We already did that. It's just different. 9.21, 9.22. Okay, you can find actually using the Graham's law, you can find the molar mass also. Okay, so but we're not doing it here. And 9.5, we discussed that already, the kinetic molecular theory of gases, we already discussed that. And then we have this kinetic energy and all that, you don't worry about that. Okay, the only thing that you need to do, I think, is the URMS. You should do that, URMS calculation. That's the only thing. So 9.23 we will do. And then leave out anything excess after that. 9.6. I mean, I covered all this in explaining, in the beginning, but we are not doing any questions that relate to like 9.24, 9.24, and that's the end of it. Yeah. Okay. All right. Let's do this URMS. That we should do. Yeah.
What about chapter 10?
Chapter 10 also, I'll show you. Just a minute. What time is it? Yeah, just let's finish this. URMS, last question. Okay, here. Calculate the root mean square velocity of a mole of oxygen molecule at. So this is the 7 and 8. So URMS of oxygen. And the temperature given is, and this is for 1 mole of oxygen, 1 mole of oxygen, and the temperature is negative 23 degrees Celsius. Okay, so 3 RT over M. So here URMS is equal to 1 minute. URMS 3 RT, 1 mole of oxygen, molar mass or you want to leave this out? I don't know. 3 RT over M, and M stands for the molar mass, and 1 mole of oxygen. Okay, here. All right, so 3 RT, URMS is 3 RT over M. Okay. All right, so leave out these problems, 9.21, 9.22, 9.24, but focus on this one last problem. So the formula this one uses is U R M S is equal to 3 R T over M. And as I showed you this in the beginning, the 3 RT over M under root, the value of R is, we are going to only for this case, we are using it at 8.314 joules per mole K. Okay, 8.314 joules per mole K.
But how would we have known to use that from the wording of the question? Because it didn't have joule. Oh, because it said velocity, huh?
Yeah, I asked to calculate the root mean squared.
Yeah, M is the molar mass. And actually, joules also has a other formula, and that joules is kilograms per meter square over second square. Joules is equal to kilograms meter square over second square. Okay, and this molar mass actually is in kilograms. Molar mass is in kilograms. So you will have to convert it like the grams to kilograms. All right. Let's get this here. Molar mass in kilograms. So here we are looking at oxygen gas. It's always important to get the identity of the gas. The temperature given is in negative. So convert that to Kelvin. So 273 minus 23, and that's 250 K. 250 K. Okay, and sorry, this would be under root. All right, so U R M S is equal to under root 3 times R. R is 8.314 joules over mole K times the temperature is 250 K over the molar mass of oxygen. Now that's the thing. Oxygen is what? 16. So one oxygen is equal to 16. So two oxygens are 32. So the molar mass of oxygen is 32 grams per mole. But convert that to kilograms. So 32 grams times 1 kilogram over 1000 grams. Okay, so 32 divided by 1000 and you get 0.032 kilograms. So this is the number you're going to use. Okay, so let's get this. So here 0.032 kilograms. Okay, now let's do this. So let's do the math here. Okay, so here I have just substituted the value of joules with kilograms, meter square, and second square, and that mole K is still going to be there. Per mole K, sorry, per mole K. So this way, it's very important to do that because you need to cancel out the units. So K and K get canceled, and kilograms cancel out, and then the moles. I think this is the moles. One second. So the moles also cancel out because the molar mass is in kilograms per mole. So this kilograms per mole. And so here we have this kilograms, this mole and this mole cancel out, kilograms and kilograms cancel out. And we are just left with the units of meters squared and seconds squared. So when you remove this under root, it automatically becomes meters per second. Okay, the rest is you just multiply the whole thing, divide it, under root, and chapter on gases done. Okay, so